Welcome to Measurement and Instrumentation. This is a foundational course that blends science, engineering, and practical application. We are going to explore the art and science of taking accurate measurements in engineering systems, not just how we measure, but why measurement is meaningful, how to interpret it, and how to ensure it's reliable. This course is split into two modules. Module 1 will cover the fundamentals, the principles behind mechanical measurements, signal characteristics, measurement standards, data treatment, the structure of measurement systems, and the functioning of detectors, transducers, intermediate systems, and terminal devices. Module 2 will cover applied measurement techniques, from counting events to measuring displacement, force, torque, pressure, flow, temperature, vibration, shock, and acoustic properties. 1. Fundamentals of mechanical measurements. Mechanical measurements involve detecting and quantifying physical quantities related to mechanical systems, length, displacement, force, velocity, acceleration, pressure, and more. The goal is accuracy, capturing the true value of a physical quantity, and precision, achieving consistent, repeatable results. But in practice, no measurement is perfect. There are always errors, uncertainties, and limitations to account for. 1.1 Why we measure. We measure for four main purposes. Control, to regulate processes in real time. Monitoring, to track conditions for safety or maintenance. Research and development, to study and improve systems. Compliance, to meet standards and legal requirements. 1.2 The nature of mechanical quantities. Mechanical quantities can be static, unchanging in time, like a constant load. Dynamic, varying with time, like vibration in a rotating shaft. The method and device we choose depend on whether the quantity is static or dynamic. 2. Characteristics of dynamic signals. A dynamic signal is a time-varying representation of a physical phenomenon. When measuring dynamic signals, we must capture not just the magnitude but also the time-dependent behavior. 2.1 Key characteristics. Amplitude, the peak value of the signal. Frequency, how fast it oscillates or changes. Phase, the timing of the signal relative to a reference. Waveform, the shape of the signal over time. 2.2 Measurement challenges. Dynamic signals can be distorted by limited frequency response of the measurement system. Noise contamination. Sampling errors if using digital instruments. This is why signal conditioning, filtering, and proper sampling rates are critical. 3. Standards of measurement. A measurement standard is an agreed reference against which other measurements are compared. 3.1 Classification of standards. Primary standards, absolute references maintained by national metrology institutes. Secondary standards, calibrated against primary standards for routine use. Working standards, used in everyday measurements in industry. 3.2 Importance of traceability. All measurements should be traceable, linked back to primary standards through a documented chain of collaborations. 4. Statistical treatment of data. When we take repeated measurements, we rarely get the same number every time. Variations may be due to random errors, systematic bias, or environmental influences. 4.1 Mean value. The average of multiple readings gives the best estimate of the true value for random error situations. 4.2 Measures of spread. Range, difference between highest and lowest readings. Standard deviation, a measure of dispersion. Variance, square of the standard deviation. 4.3 Error types. Systematic errors, predictable and correctable. Random errors, unpredictable variations. Gross errors, mistakes in reading or recording. 5. The generalized measurement system. A measurement system can be viewed as three main blocks. Detector, transducer stage, senses the physical quantity and converts it into a usable signal. Intermediate modifying system, conditions the signal, amplifies it, or changes its form. Terminal stage, displays, records, or stores the measurement. 6. Detector and transducer elements. A detector senses the quantity of interest. A transducer converts it from one form of energy to another, usually into an electrical signal. 6.1 Types of transducers. Active transducers generate their own signal, e.g., thermocouples. Passive transducers require an external power source, e.g., strain gauges. 6.2 Performance characteristics. Sensitivity, range, resolution, response time. 7. Intermediate modifying systems. These systems adapt the signal for transmission and interpretation. 7.1 Examples. Amplifiers increase signal magnitude. Filters remove unwanted frequencies. Modulators encode signals for transmission. 8. Terminal devices. These present the measurement to the user. 8.1 Types. Analog displays, dials, meters. Digital displays, numerical readouts. Recorders, paper charts, electronic logs.